So this next section starts looking at tying electrochemistry together with some of the principles we looked at in thermodynamics, specifically equilibrium and free energy. Let's look at free energy first. So we know that a reaction with a negative delta G is spontaneous, and a cell with a positive E0 cell is also spontaneous. And so there has to be some link between those two properties. And it turns out that those properties are linked by work. We're not going to go through the derivation, but this is basically where we end up. We can say that delta G is equal to minus NFE, where E is equal to your E0 cell. F is equal to that Faraday constant down there, 96,485 coulombs per mole. And that N is the same N that we had earlier. That's the number of electrons transferred during the redox reaction. So again, that's the number of electrons, that lowest common multiple that you had to get when balancing your two half reactions so that the electrons canceled. So however many electrons you needed to have in order to have them cancel, that's your value of N. So we have a delta G under standard conditions is equal to minus NFE0 under standard conditions. Or if we're under non-standard, we can say that delta G is equal to minus NFE, where E is non-standard. We haven't really addressed non-standard E cell yet, but we will get there eventually. I mentioned also that electrochemistry is linked with equilibrium. So we can expand our idea a little bit farther of this link by looking at the relationship between E0 cell and equilibrium. So we saw earlier in our thermodynamics chapter that delta G0 is equal to minus RT natural log of K. And we know that delta G0 is equal to negative NF E0 cell. So we can set those two things together and we get minus RT natural log of K is equal to minus NF E0 cell. So these two quantities are now equal, and we can rearrange those to solve for any of those variables that we want. Here we just I showed an example where we solve for E0 cell. So if we know the K for a redox reaction, we can solve for the E0 cell. Vice versa, if we know the E0 cell, we can solve for K. We can take this a little bit farther if we know we're under standard conditions and at 298 K. R here is the gas constant, so it's our 8.314 joules per Kelvin mole. Temperature at Kelvin. If we're at 298, both of those become a constant. F, of course, is the Faraday constant, so it's also a constant number. So we have these three values right here that become constants at a given temperature, and we can work those values into a predetermined equation here. Now these two equations are exactly the same. The only difference is that this first one uses the natural log, this bottom one uses the common log. Other than that, they are exactly the same. Okay, and they're like a lot of the things we've done in this this particular lecture. It doesn't matter which one you use, you will get the same basic answer for either one of those, and there's no situation where one is correct to use and not the other. Okay, it just depends on which log function you want to use. Now there is some rounding that takes place to get this 0.0257 and this 0.0592. So it is possible that your numbers will vary by a decimal point here and there, but it's not too big a difference. So all those constants work back in, and other factors work back in to give us our volts. And there's our N value, because that, of course, is going to be determined by the individual reaction, so that cannot be a constant. So here's one I'd like you to try. Calculate the value of K for the oxidation of iron by H plus at 25C. So it's already balanced for you. You should be able to figure out the number of electrons that are transferred. Specifically, you can probably do it fairly easily using the iron there. For calculating the number of electrons that are transferred, you do need to keep in mind the stoichiometry there. The other thing you are going to need to find here is your E0 cell. And once you find that using the tables in your book, you should be able to use the previous equation to find the value for K. I will have that worked out on YouTube so you can see if you did it correctly. So let's tie all of this together here. We know that when delta G is negative, if K is greater than 1, or if E cell is positive, the reaction position will favor the products that will move in the forward direction. If delta G is 0, K will be 1. E cell is 0. That means that the reaction position is at equilibrium. This is kind of an interesting thing here. So when a battery dies on you, it hasn't actually gone to completion. It has reached equilibrium where the forward reaction and reverse reaction is occurring at the same rate. What that means is that you have no net movement of electrons, so you have no voltage taking place. And then if we have a positive delta G, our K is going to be less than 1. Our E cell is going to be negative, and those reactions favor the reactants. So we can look at the reaction position in terms of spontaneity, in terms of equilibrium constant, and now for a redox reaction in terms of E cell. And all of these factors are linked together by equations. Again, you can manipulate these any way you want. We've got the link between delta G and E0 cell here. We've got the link between E0 cell and K. And again, this just used the common log one. There's no reason you can't use the natural log one. It's the same equation. And here we have delta G equals negative RT log of K, natural log of K. So that's our link between delta G and K. Okay, so all of those three factors are linked for all these different types of reactions.